I often reminisce about when I was a young, naive university student, and the professor at the time was demonstrating how to run a certain Python script. I remember writing the exact same code as him, line by line, but when I tried to run it, it kept failing. I was completely bamboozled because why would it run so smoothly on my professor's machine but inexplicably fail on mine? Naturally, I went to his office hours to make inquiries, and there, I replicated the same steps, wrote the same code, ran it, showed him the failures, and do you know what he says? I don't know, it works on my machine. He could not care any less, and that day I solemnly swore to never attend office hours again. I tried to troubleshoot the problem on my own, but I kept getting these weird cryptic errors which seemingly had no relevance to the code itself as opposed to the ecosystem that the code was running in. So I had no idea what the culprit was. What did I do? Erased everything from my computer, nuked every single file and process that was running in it, and then from a clean slate, I recreated the code, ran it, and it worked. Until this day, I still don't know what it was that I deleted that was poking and prodding at my application. This idea of an application failing because of disturbances in its environment has actually plagued developers for many years. In the early 2000s, developers tried to tackle this issue by running their application inside of a virtual machine. A virtual machine isolates your application, allowing it to run in a controlled environment and basically shielding it from any disturbances that may infiltrate your application. But the problem with virtual machines is that they replicate your computer's operating system, which makes them very heavy and resource intensive. But big companies still needed their servers to be able to run many applications, so what did they do? Spent a lot of money on powerful servers that can support many virtual machines, in turn reliably running many applications. But scaling these servers was simply too expensive and not very feasible. Big companies were drowning in energy bills and hardware costs. But then in 2013, Docker came out and it changed the entire landscape. Docker, what it does is it provides an ecosystem that allows developers to run their application inside of a container. A container is an isolated environment because it contains your application's source code and only the resources that the application code needs to run, nothing else. This ensures that your application will always reliably run and behave the same way whether it's running on a MacBook Pro, a Linux server, or your grandmother's typewriter. It doesn't matter. But what's different between Docker containers and virtual machines, the contrast is that Docker containers are small and lightweight. You can seamlessly run multiple containers on a single server. It's no surprise that big companies wasted no time phasing out virtual machines in favor of the more scalable Docker containers. The ability to run an application inside of a container is a very necessary and in-demand skill in the present day. That's why I created this course, which is divided into 10 different chapters. In Chapter 1, we're going to be setting the stage for the remainder of this course. Every lesson in this course is connected to a starter project. I also uploaded exercises that you can use for extra practice once you're done the course. And all of these resources, the starter projects and the exercises, I uploaded all of them inside of my GitHub repo, whose link you can find inside of the video's description. So go to my GitHub repo now. Feel free to pause the video until you do so. Okay, once you're there, what I want you to do is click on this big green button that says code or whatever it may say when you're watching this video and download zip. Once you download the zip file, feel free to extract its contents. And inside of the resources, you should see two folders. Let me zoom in a little bit. Okay, the first folder contains all of the starter projects for this course. And the second folder should contain exercises that you can use for extra practice once you're done the course. So that's it for chapter 1. We're just setting the stage for the remainder of this course. In chapter 2, we're going to start by installing Docker into your machine. All right, I will see you there. Welcome to chapter 2. Here we're just going to be installing Docker and signing into Docker Hub. Fairly simple stuff. So go to whatever search engine you like to use. I'm simply going to Google the keywords install Docker. And we're going to be installing the Docker engine into our local machine. Choose whatever link corresponds to your operating system. I'm using a Mac with an Apple Silicon chip, so I'll be choosing this link. This should go ahead and download a DMG file if you're using a Mac. An exe installer if you're using Windows, doesn't really matter. Click on whatever installer you downloaded and go through the steps in your installation wizard. In this case, it just wants me to drag the Docker application into my applications folder. If you're using Windows, just go through whatever steps are given to you. It's copying Docker to applications, so I'll give that a couple of seconds. All right, it's a big 2 GB download. Go to my Launchpad, see if Docker showed up. And as it verifies Docker, it should automatically start running the Docker engine momentarily. Let's go ahead and open it. All right, as it stands, the Docker engine is officially running on my computer. I can confirm this by going up top, seeing the Docker logo that says Docker Desktop is running. If you're using Windows, you should see something similar on your bottom right toolbar. Anyways, I'm going to sign into Docker because we're going to be pulling a lot of artifacts from Docker Hub. More on that later in chapter 3. Anyways, I'm going to continue with Google because I already have an account. If you don't, make sure to sign up for a Docker account. All right, I'm almost done. Open Docker. I'm fully verified, and now I should be good to go. If it prompts you to do a survey, feel free to fill out the survey or skip it, doesn't matter. But make sure to install the Docker engine on your machine, sign into Docker, and that should be it. We should be good for chapter 3, where we're actually going to start using Docker, in this case, to run a Python app inside of a container. But before we get to the meat and potatoes of this course, I'm going to take a small break and brace myself by grabbing a cup of coffee, and I will see you in a bit. In this chapter, you're going to run a Python script without actually installing Python itself. Why would this be useful? Depending on the machine that you're using and the operating system that it's running, the process for installing Python is going to be different. Some installations might be very seamless, others might be a little bit more involved, and others might simply keep failing because the system is just not compatible with the Python package itself. Now, Docker ensures that the process is consistent regardless of the machine that you're using. That's because when you use Docker, nothing is installed into your system. Everything happens inside of Docker itself. The process is as follows. Python is composed of 3 major parts: the interpreter, the standard library, and the Python package manager pip. What developers did is they took a snapshot of their Python environment at a specific point in time. This snapshot is called an image. Where did developers upload this image? Docker Hub. Docker Hub is a global registry that contains Python environments, Java environments, Haskell, you name it. What I can do is, from Docker Hub, I can pull the Python image into my local Docker cache. The Python application that I want to run using Docker is somewhere in my computer's file system, somewhere in my host machine. So using Docker, I can create a Docker container. And then I can mount the Python application from my host machine into the Docker container where it can access the Python environment that we pulled. Then I can run my Python application using the pre-configured Python environment. Once the application is finished running, once it's done executing, I can destroy the container. And if I decide, hey, you know what? I don't really want to use Python anymore, I can destroy the image as well. I can remove it from my Docker cache. And it's like it never existed. Let's put all of that into practice. All right, let's start by going over to Docker Hub. Write Docker Hub inside of your favorite search engine. Click on what is probably going to be the first link. That should take you to the Docker Hub homepage. Make sure that you're signed in using the Docker account from Chapter 2. I already am. Once you do ensure that you're signed in, we're going to search for the Python repository. Okay? The Python repository contains hundreds or however many different Python images, each one tagged with a specific version. If I just say docker pull Python, what that's going to do is pull the latest version of Python or the latest image that was uploaded to this repo, but we don't want to do that. For the sake of example, what I want to do is pull the Python 3.8 slim image. Okay. And if I press enter, what that's going to do is pull this image from Docker Hub into my local Docker cache. I can enter the command docker images to view the list of images inside of my Docker cache. And here we see the Python image tagged 3.8 slim. And this image bundles together a lightweight Python environment. And if you think about it, how easy was that? All we had to do was say docker pull, and it didn't install anything in our system, as opposed to installing it inside of Docker itself. Okay. Now the next step is to create a container using the command docker run. The container is where your application is going to run. So we need to mount our application's code from your computer's file system into the Docker container itself. So what you're going to do is put your file explorer on one side containing your project and a terminal on the other side. So if you're using a Windows computer, put your PowerShell or command prompt. Drag the folder containing your Python app into your respective terminal. That should give you a path. If you're using Windows, your path is going to have backslashes. Please replace it with forward slashes instead, because that's what's recommended to be used with Docker. Okay, and then we're going to use the command or the flag -v, I should say, which stands for volume mount. And what that's going to do is mount our project from this path in my computer's file system into a path of my choosing inside the Docker container. So I'm using a colon to separate the path where my project already exists and the path where I want the project to be mounted. I can put this pretty much anywhere, so followed by a front slash, I can specify any path inside of my container. Let's say source/app, doesn't really matter. And now the container that's going to run my Python application at this path, it needs to access a Python environment. And it can do so by referring to the Python image that we pulled. So Python, followed by a colon, we specify the tag 3.8 slim. It's going to be able to refer to this image and access its underlying Python environment. And now it's got the Python application, it's got the Python environment to run it. The final step is to provide the container with a command that it can use to actually execute the application. Sorry about that, guys. My recording just randomly stopped. Anyway, the final step is to provide the container with a command that it can use to actually execute the application inside of it. So it's got the application mounted at this path. It's got the Python environment that it needs to run the application. And if you've run a Python application before, you would know that the way to run it is just to say python filename.py. The container understands that the application is at this working directory. So we need to say Python source slash app slash whatever the file name.py is. So Python app.py. Fingers crossed, that was a lot of work. Let's make sure it works. Beautiful. That's all. I just used a pre-configured Python environment to run my Python code inside of a Docker container. Now, after the application is finished running, the container is stopped, but it's not destroyed. So what I can do is say docker ps. What that does is it shows me the running containers. Obviously, we don't have any, but I don't want to have any loose containers in my Docker engine. So I'll say docker ps-a. This shows me all the stopped containers as well. So the container we just created, it has the container ID 71E whatever. And let me zoom out a little bit just so you can see it all in one line. And it was given the name tender mayor. What I can do is say docker rm. This is a command that is used to remove stopped containers. I can either remove the container by referring to its ID or to the name that was given to it. I'm going to use the ID because that's usually how it's done, but you can also remove the container by referring to its name. All right, now if I say docker ps-a, no more container. Now what I can do is clean up by removing the Docker image. So Docker images shows me that I have a Python 3.8 slim image inside of my Docker cache. I can remove an image by first saying Docker image, followed by rm. And I can remove the image once again by referring to its ID or by saying Python 3.8 slim. It's easier to just use the ID. All right, and if I say Docker images, no more image, no more container, and it's as if it never existed. How easy was that? All right, that's all for chapter 3. And in this chapter, things were a bit tedious because we did everything inside of a terminal. Chapter 4 is going to simplify and organize our workflow a little bit more by using a Docker file. So I will see you soon. In this chapter, you will expand on the Python image that we pulled from Docker Hub. In chapter 3, we combined all of the container's instructions into a single command. This approach, although common, is just a little bit messy. The solution is to take the Python image that we pulled from Docker Hub and expand on it. So the Python image is the base image because it forms the foundation onto which additional layers can be added. The remaining layers of our image will tell the container what to do. The second layer will specify the path where the container will run your application, also known as the working directory. The third layer will tell the container which application it needs to copy into the working directory. The fourth layer specifies the commands that the container will use to actually execute the application. This image, as it stands, is a blueprint that describes how the application is supposed to run. The container will inherit everything inside of the image and actually run the application. In this scenario, what it's going to do is use the provided commands to run the application that exists at the working directory using the inherited Python environment. Let's have a look. Welcome back. Here I have a text editor open as well as my starter projects. I'm using Visual Studio Code. You can use whatever text editor you want. Whatever it is you end up choosing, launch the second starter project from the lessons folder into your text editor. I am going to zoom in because things are just a little bit too small. Should be fine. All right. So here we have a Python application and inside of the exact same directory, a Docker file. We can build our Docker image using this Docker file. And the first layer is always the base image. So from is a Docker command that sets the base image. And the image that we're going to pull from Docker Hub is called Python 3.8 slim. So we're going to be pulling an image from the Python repository tagged 3.8 slim. Simple enough. The second layer describes where the project is going to run inside the container. This is also known as the working directory. Now, workdir is a Docker command that allows you to specify the working directory of a container. And we're going to set this to be something like source/app. That's my default. Okay. And now let me minimize this. All right, so as I was saying, the third layer copies your application into the working directory. So copy is a Docker command that we can use to copy the application Python app.py into the working directory source/app. But instead of writing this all over again, what we can do is in the second argument of our copy command, if we put a dot, Docker is going to know that we're referring to the working directory that we established in step 2. So that's what this dot means when you place it as the second argument of our copy command. The dot means something totally different if you place it over here. Anyways, we'll get to that later. The fourth layer specifies the commands that will execute the application. CMD allows you to specify the command as an array of strings. So if the command is going to be Python source/app/python app.py, then here we have to say Python as one argument, separated by a comma. We're going to be running the application that will live inside the working directory source/app/python app.py. Okay, looks good to me. Inside of a terminal, we can enter the command docker build. What that's going to do is build an image from the Docker file that we just created. -t assigns the image a name. We can call it something like Flask application. And we can tag this image to have a version of, 0.0.1. You can give it a version of latest, whatever. And the dot at the end of a Docker build command basically says, look inside of the current directory for a Docker file. It's going to find a Docker file inside of starter code, inside of the current directory. So what it's going to do is build an image from it. The first thing it's going to do is, based on the first layer of our image, pull Python from Docker Hub. As you can see over here, that's the first layer. And the second and third steps, it's going to establish the working directory, copy the application into the working directory, and then it's going to provide the relevant commands to the container that is created from this image. Okay, so now let's actually create a container from this image. We can do this by saying docker run. Actually, before doing that, what I want to do is say docker images to view the image that we just built. You can ignore the things I have over here. You should probably just have this. Now it can create a running container from the Docker image by using the command docker run. I can create a running container from this image by using the image ID or by specifying the full name. I'm just going to go ahead and specify the full name for reference. So Flask application, tag 0.0.1, fingers crossed. And the container executes the application inside of it. Pretty simple, don't you think? So that was a fairly simple use case, a container executing an application mounted at a certain working directory using a Python environment that was pulled as the base image. In the next chapter, we're going to be packaging up a web application and then running that inside of a Docker container. That's going to have some extra moving parts, but it's not too complex. Anyways, I will see you in chapter 5. In this chapter, you will run a web application from inside of a Docker container. A web application contains numerous files of code which rely on dependencies in order to compile. We need to create an image that captures the application source code, installs every single dependency that the code relies on in order to compile, documents the port that the application runs on, and pulls the environment that the application needs to run. So the web application needs a Python environment in order to run. So what we can do is pull the Python 3.8 base image from Docker Hub. The base image forms the foundation onto which additional layers of our overarching image can be added, which means the second layer will specify the path where the container should mount the web application. Remember, this is also known as the working directory. The third layer of our image is going to tell the container which files it needs to copy into the working directory. One of these project files is a text file that contains a list of dependencies that the application depends on in order to compile. So the fourth layer is going to use the run command to actually install every single dependency that's listed inside of that file. The fifth layer of the image is going to provide documentation. This step will do nothing except inform the developer which port inside the container the web application is going to use. The final layer, as always, is going to provide the container with commands that it can use to actually execute the web application. This image that you see here is a blueprint from which a container can be created. The container actually mounts the web application source code into the working directory, inherits the dependencies that the code relies on in order to compile, the environment that it needs to run, and the commands that it will use to actually run the application. After everything is set up, the container uses the provided commands to run the web application that exists at the working directory using the inherited Python environment. The image also documents which port in the container the web application is using. Using this information, I, the developer, can map the container port to a port on my machine. This allows my browser to actually access the application because it will make a request to a port on my machine, which is connected to the port that the app is using inside of the container. Let's put all of this into practice. All right, welcome back. So once again, I've got all my starter projects on one side, my text editor on the other. I'm just going to go ahead and drag the third starter project into my text editor. Once again, feel free to use whatever text editor you like. I'm using VS Code. Anyways, as before, we can build our Docker image using a Docker file. So using the from command, we can set the base image. And the image that we're going to pull from Docker Hub is Python. We're going to be pulling it from the Python repo, and it's tagged 3.8 Slim, the Slim version of Python 3.8. All right, we can use the work dir command to specify the path where the container will actually run your project. I'm just going to stick to source/app. You can use whatever path inside of your container. The next layer is going to tell the container to copy all of these project files into the working directory. So here I'm going to say copy. The first dot argument refers to every single project file inside the same directory as the Docker file. The second dot argument refers to the container's working directory. So this line reads, copy every file in this directory into the container's working directory. All right. Now, Docker provides the run command to specifically run installations during the image building phase. The image that we're currently building can leverage the Python environment to run the Python package manager pip. Install all the requirements inside of requirements.txt, or I should say flask demo/requirements.txt. So what this line is going to do is during the image building phase, get all of the dependencies inside of the requirements.txt file and install them so that the code inside of the container will have direct access to them. Okay, the fifth layer of our image is simply going to provide documentation. So the expose command will inform the developer, whoever is going to be creating a container that runs the application, that the underlying application will be using port 5000 of their container. How do I know that? That's just because the application was programmed as such. The person running the container probably won't have access to the code. So we're just providing them that documentation so that they will know how to serve requests using this app. All right. The final layer provides the container the commands that it can use to actually execute the application. So CMD, inside of it, we're going to define the command Python work directory slash flask demo slash app.py. Now, because Flask demo is going to be a subdirectory that will live inside of the container's working directory, we can just say flask demo slash app.py, and it should be smart enough to find it and execute our application's entry point. All right, that's pretty much it. Let's go ahead and spin up a new terminal session. And actually, before I continue with this, I just want to make sure that you do not confuse run with command. Run installs dependencies inside of the image itself. Command tells the container how to execute the application. And it's usually the last step after a complete snapshot of the application and the environment has been set up. So while the image is being built, run installs all the dependencies that the application is going to need when it's running. These commands are going to be used once we create a container to actually run the application. All right, we could probably get rid of this slash. Looks nicer to me at least. Okay. And we can build this snapshot into a Docker image using Docker build. -t. I'm going to call the image that we build from this Docker file Flask demo, tagging it 0.0.1. And remember that if you put a dot inside of your Docker build command, what that's telling it is look for a Docker file inside of the current directory starter code. It should be able to find it and build an image from it. All right, so during the image building phase, here you can see it ran pip install -requirements.txt and installed all the dependencies that the application is going to rely on. It also pulled the Python image from Docker Hub as we expected it to. So here we have all layers of our image, as well as the image itself providing the commands that the application is going to rely on. I'm going to say Docker images to make sure that everything is working properly. Beautiful. If you have any other images other than Flask demo 0.0.1, make sure to delete them the way I showed you before, Docker image rm, pasting in the image name or the image ID, whatever you want to do. Anyways, my cache is pretty clean, so I'm going to go ahead and say Docker inspect, and I'm going to inspect the following image. Let's use the ID just to change things up. Docker inspect the image with this ID. And the image is telling me, the developer who will be creating a container from this image, that the underlying application is going to be serving requests on port 5000. This is very valuable information for me because now when I create the container, Docker run, I know that my application is going to be serving requests on the container port 5000. So I can map the port in the container that the application is using to any port on my machine. So the first one refers to the machine port. The second argument after the colon refers to the container port. And I'm going to create a container from the image that we called Flask demo 0.0.1. I can also use the image ID, but I like to vary things just for you. Let's try it out. Strange. It seems that port 5000 of my local machine, not of the container, is already being used for whatever reason. I must have another process running on my computer. So what I'm going to do is map the container port 5000 to, let's say, localhost 3000. Okay, that should work fine. So now by making a request to port 3000 of my host machine, the application will be able to forward a response through its container port. So let's say localhost 3000. Wonderful. All right, that was it for chapter 5. In chapter 6, we're going to be wrapping all of this up by pushing everything to Docker Hub. But before we do that, what I want to do is clean up. I'm just going to delete the container. So Docker PS, oh, we don't have any running containers. Let's say Docker PS-A. We've got 2 stopped containers, or at least I do. I'm going to delete both of them. Docker RM, just so you can see it better. I'll delete the container with this ID. And just to vary things up, Docker RM, I'm going to delete the container with this name. If I try this again, Docker PS-A, no more stopped containers. We still have our image. All right, now let's go ahead and delete the image. Docker RM flask demo 0.0.1. Docker images, make sure everything is good. All right, I think we're ready for chapter 6. I will see you there. In this chapter, you will push your own image over to Docker Hub. After spending so much time creating your application, you want everybody on your team to be able to run it, to be able to test it. So you package it up into an image that contains the application's source code and only the resources that the application needs in order to run. Then you go ahead and push it over to Docker Hub. From there, anybody should be able to pull this image from your Docker Hub registry and create an isolated container that can run the application. Let's have a look. All right, once again, I've got the file explorer on one side, a text editor on the other. I'm just going to drag the 4th starter project from our lessons resources. So I've got a Docker file that's already been created for the following grade submission application, which is a Flask application. And the idea is that I'm working in a team of developers, right? And they want to be able to run this Flask application inside of their machines. So what we need to do is push an image that captures a snapshot of this application and the environment that it needs to run inside of a global Docker Hub repo. They should be able to pull this image from my repo and run it inside of their respective Docker engines. And the idea behind this is that because they're running our application inside of an isolated container, all of our testers should be able to successfully run the app. The app should behave the same way regardless of the machine or the operating system that they're using. So enough preamble, let's go ahead and build this image first and foremost. Docker build-t. And now what I want you to do is on Docker Hub, take note of what your username is, because we're going to start by putting in the username followed by a slash. Then we're going to name our image something like, I don't know, grade submission. And we can tag it something like Flask 0.0.1. Tag it whatever you want. And remember, the dot means current directory. So this is telling the Docker build command to look for a Docker file inside of the current directory. It's going to do that. It's going to find it. It's going to build an image. All right. And we're going to be pushing this image to Docker Hub. So I'm going to say Docker images. And I'm going to say Docker pushing the following image tagged Flask 0.0.1 to Docker Hub. All right. Now if I refresh my list of repositories, I see a grade submission repository with at least one image tagged Flask 0.0.1. So my team of testers, they're going to see that this is version 0.0.1 of the Flask application that we pushed. And now we're going to take the position of testers. We're going to assume that we've never been exposed to this image prior. So what we can do is say Docker image remove, removing this image from our local Docker cache because it wouldn't make sense for us to have access to it beforehand. Okay, clear. And one of my testers, what they would do is they would go to the tags view and they would copy the following pull command to pull version 0.0.1 of our Flask application. All right, and they probably wouldn't have access to all of these project files, so I'm just going to close it and maximize this terminal. They have no idea what port the application is running on, so what they would do is something like this. They would inspect the image. Okay, and they would see that the image is running on port 5000 of the container port. So looking at the metadata, what they can do is create a container, docker run, and they can map the container port that the application is serving requests on to some random port on their host machine. I don't know, say 2471, and create a container from this image, a container that's going to run the Great Submission app. Now the image itself is the following. All right. Now 2471 is just a random port that I chose. You can choose something more or less random. So if I go to localhost 2471, beautiful. As the tester, I was seamlessly able to run this application inside of my Docker engine. So I can submit a grade for potions. I can test to see if this application actually works. Everything works beautifully. So the idea is that when you push an image to a registry, anyone should be able to create a container from this image and run whatever underlying application is inside this container in a very reliable way. All right, that is it for chapter 6. I will see you in chapter 7, where we start talking about environment variables. In this chapter, you will learn about environment variables. The only thing that should be inside of your code base is logic. Something like a database name and the credentials needed to sign into that database is sensitive information, and it should never be written directly inside of your code base. The application should depend on the environment that it's running in to provide it with this data. The environment, a Docker container in this case, can pass this data into the application in the form of environment variables. Let's have a look. Before we start, I want to make sure that we're starting off on a clean slate. So run the command docker system prune -a. This is a pretty extreme command to run because it deletes all stopped containers, all networks, all images from our Docker environment. I'm going to continue. It deleted quite a bit of stuff for me, but if I go to Docker images now, as well as Docker ps-a, I've got no images, no containers. We're off to a clean slate. And let's begin our lesson. So here I've got my text editor and all of our starter projects. I'm going to go ahead and launch starter project number 5. We're making a lot of progress. Okay, don't care much for the application itself right now. Just going to zoom in a little bit. Don't need this anymore. All right. So the Docker file needed to package this application is already complete. We can go ahead and just package this application into an image. So docker build -t. We can call the image Flask MySQL, tag it with latest or whatever. And we use the dot to specify that the Docker file is inside the current directory. It's going to build an image from this Docker file that captures a snapshot of this application and the environment that this application needs to run. Okay, very good. And now from this image, we can create a container that executes the Python application. So docker run. And actually, before doing that, I'm going to say docker inspect. We're going to inspect the image that we just created, the application is documented to serve requests on port 3000 of the container. So before creating the container, we can say docker run -p. Whatever requests are being served on port 3000 of the container, we're going to map to, I don't know, port 8000 of our machine. Doesn't really matter. And we're going to create a container from the image, which I believe we called Flask MySQL latest. The application inside of the container fails. Why does it fail? Because it relies on environment variables being passed into it from the environment itself. Now, normally the developers would tell you what the environment variables are, but in this case, what we're going to do is just look into the code itself and see what environment variables this application relies on. The code is also very simple, so not a big deal. So here we can see that the Python application depends on the environment that it's running in to provide it with a host, a user, a password, and a database. We can create a container that maps the container port to a machine port and provides the application with the variables that it needs in order to run. The first variable that the application is asking me for is the database host. The host tells the client application which network to go to in order to find an instance of MySQL. I expect that when we eventually install MySQL, it will be connected to my host machine's network, to my computer's network, on port 3306, which is the default for MySQL. So you might be thinking, hey, we can just tell the application to look inside localhost. So I can set the environment variable or database host equal to local host. But from the application's perspective, which is going to be local to an isolated container, local host refers to the container itself, not the entire host machine. That's why Docker actually provides a special field called host.docker.internal, which translates to the host machine's network. The application is going to be able to use this information to look for a MySQL server inside of the correct host. If it finds one, it's going to need a username and a password in order to authenticate against one of its databases. So we can say -e. We're going to set the database user equal to user, create another environment variable called database password, which we're just going to set equal to password. We're going to give the application another environment variable called database name, called DB. So basically, the database host is going to help the application find an instance of MySQL by going over to the correct network. Database user, database password are the credentials that the application needs in order to authenticate against one of the databases inside of the MySQL instance that it connects to. So we don't really care about the logic that the application uses in order to do all that. All we have to do is, as the people running the application, provide it with the information that it needs in order to do so. I expect that when we eventually run MySQL, MySQL is going to have a database called DB, and that database can only be accessed with a username of user and a password of password. So let's go ahead and just run the container, and I'm going to navigate to localhost 8000. And I'm going to navigate to localhost 8000. If I zoom in, and the application failed to connect to an instance of MySQL, but here we can see that we gave it all the environment variables that it needs to do so when we eventually run an instance of MySQL. It has the correct database host, it has a username and password that it can use to authenticate against a database called DB. So in chapter 8, we're going to be setting up MySQL. For now, just keep the container running with the application running on this port, and I will see you soon. In this chapter, you will run MySQL in a Docker container. Installing MySQL directly inside of your machine, inside of your system, is really annoying. Depending on your system, you may have to configure user privileges, security options, and other detailed settings before you can finally get it to work. Once it becomes so deeply rooted into your system, uninstalling it and cleaning up afterwards is just as much of a pain in the butt. There has to be a better way, one would think. Well, thankfully, Docker Hub provides an image that contains a pre-configured MySQL environment. From this image, as you can probably guess, I can create an isolated container that runs the MySQL application. That same container can pass environment variables into MySQL to initialize a database that expects certain username and password credentials. Once you're finished with your MySQL application, cleaning up is as simple as stopping the container, removing it, and deleting its image from your Docker cache. And just like that, it's like it never existed. Let's have a look. Alright, starting from a new terminal, the MySQL image that we're going to pull comes from the MySQL repo from Docker Hub, and the image is called MySQL Server version 8. All right, go ahead and pull this image into your Docker cache from Docker Hub. And from this image, we're going to be creating a container that runs MySQL. And within MySQL, we need to initialize a database called DB that is supposed to expect this username and password. The reason we're going to have MySQL initialize such a database because we already have a Flask application trying to connect to it. Right now, there is no MySQL instance, so we're going to be working on that. So looking at the documentation, we can see that from our container, we can pass the following environment variables into the underlying MySQL application. So going back here, I can say docker run. The MySQL app is going to be expecting these three variables. So MySQL database, which we're just going to set equal to db-e, MySQL user, which we're just going to set equal to user, MySQL password, which we're just going to set equal to password. And we're going to create a container from the image that we just pulled from Docker Hub. All right. And with a simple Docker command, you now have a running instance of MySQL. All right. Oh, I forgot to do something. The MySQL application is running on port 3306 of our container, but I forgot to map the container port to a host machine port. If we don't map it to the host machine port, our application won't be able to access it because it was programmed to look for our MySQL instance within our host machine's network. So make sure that you map the container port to the host machine port, otherwise it's not discoverable. For some reason, I can't stop this process. I'm not sure I Control Z. All right. Let's try this again. This time, mapping the container port 3306 to a port on my machine. So -p 3306 3306. All right, should be good to go. Trying it out now. Beautiful. Our application was successfully connected to that instance of MySQL. We provided it with the information to look for the MySQL server inside the host machine, and upon finding it, use the correct username and password to authenticate against its database DB. The MySQL server, on the other hand, is discoverable at the host machine's network because we instrumented it as such, and it has a MySQL database DB that expects a certain username and password. So we were able to set all that up without installing anything into our system. And if we want to delete everything and clean up, all we have to do is say docker. Here, wait, let me close this as well. Docker system prune -a. This gets rid of pretty much everything. So if I go to Docker images, it did not get rid of the MySQL server. That one is a little bit more resilient. So let's just remove it manually. Docker image rm will remove the image with the following ID. Unable to delete images being used by a running container. All right, that makes sense. So even though we stop the docker run command, the container is still running in the background. So what we can do is say docker ps. I'm going to zoom out. Sometimes it just takes a little bit more work to clean up, but it's always worth doing so that you don't have things running in the background taking up valuable memory. So docker rm will remove the container with this ID. Or sorry, we should stop it first. Okay, docker stop the container with this ID as well. Okay, now that both containers have been stopped, we can remove them. Docker rm. Now I can go back to Docker images, delete this image as well. Docker image rm. All right. If I say Docker images now, Docker ps-a, everything has been cleaned up. We have no more loose containers, no more loose images. We were able to run a Flask application and connect it to MySQL so seamlessly, and then we cleaned everything up and it's like nothing ever happened. All right, now although we were able to do this in such an easy manner, it was a bit tedious running a Flask application on one terminal and running MySQL on another terminal. In the next chapter, we're going to look at a more simplified ways of being able to run multiple containerized services at once and being able to manage them at the same time. So I will see you in chapter number 9. In this chapter, you will create a multi-container environment with Docker Compose. Docker Compose allows you to configure multiple containers at the same time. In the previous chapters, you wrote 2 separate commands. The first command creates a container that runs the Flask application, and the second command creates a container that runs MySQL. Running and managing 2 containers separately is really annoying and cumbersome. Docker Compose creates an environment where multiple containers can seamlessly communicate and run alongside each other. It follows that you can configure both containers inside of a single file, where each container is responsible for what's called a service, your application in this case. The first container will run a MySQL instance, a MySQL service, and the second container will run a Flask service, a Flask application. You can name the containers whatever you want. The MySQL container will be created from the MySQL image that we previously pulled from Docker Hub, and the application container will be created from the Flask application image that we created ourselves. Under environment, you can specify the environment variables that each container will pass to its underlying application. The MySQL container will authenticate users against a certain username and password in order to access its database DB. The Flask application will try to connect to a database being hosted inside the MySQL container, and we can provide it with the credentials needed to authenticate against the database DB. We can also map the port that each container will run on and control which container runs first by saying that the Flask container depends on the MySQL container. Next, calling Docker Compose up will create both containers, starting with MySQL, And then I can destroy both containers all the same by calling docker compose down. That is just beautiful. Let's have a look. All right, once again, I have starter code number 5 opened up inside of my text editor. We're not quite done with it just yet because it does contain a Docker Compose file that we need to investigate. First and foremost, what I want you to do is recreate an image from this Docker file. I've already got the command set up, so I'm just going to enter it. All right. Docker images, so we can have quick access to the image name. All right, we're good. So going to my Docker file, under the, let me zoom in and reduce this. Under the services field, we have a container called MySQL and another container called Flask app. It follows that the MySQL container will be running a database service, and the Flask app container will be running some sort of web application, which in this case was a very simple web app that just connects to MySQL. Anyways, you've seen the application before. Now you can basically rewrite the commands from earlier as fields in a Docker file. And what I'm going to do is get the command that we created earlier for MySQL and temporarily copy it over here with comments, of course. I'll be deleting it shortly, don't worry. So under the image field, you need to specify the image from which the container will be created. This is going to be the MySQL image version 8. All right, so we've got that set up right over here. Now under environment, we can specify the environment variables that the container will pass to its underlying application. Remember that these will be, I'm just going to copy those so that I can have access to them on top. MySQL DB, MySQL user, and MySQL password. Removing the comments. Under ports, you can specify the port mapping between the container and the host machine. You'll remember that we had that set to 3306, 3306. All right, fairly simple. You know what? I'm going to wrap all of these up in string quotes as well. If you intend on something being a string, wrap it up in string quotes. Okay. We're basically done with this command. And what I'm going to do is pull the command that we used to create a container for our Flask application. So I'll be copying that over here with a nice little comment. Okay, under the image field, we can specify the image from which the container will be created. So the one that we actually just created, Flask MySQL latest. Okay, and now under environment, you can specify the environment variables that the container needs to pass into the Flask application. So we're going to take the environment variables from earlier and pass them into our app. So the database host in this case, by the way, one thing I should have mentioned is that you should really watch your spacing when you're inputting stuff in YAML. So make sure that your indentation is correct. Otherwise, things are not going to function properly. You can probably download a Docker extension into your VS Code editor. I'm just going to continue, but again, please do make sure that your indentation is good. And so you'll remember that the database host helps the application identify where there is a running instance of MySQL, which network it should look in, where it should look. In this case, the running instance of MySQL is inside the same network as the Flask app. They're both inside of the same Docker Compose environment. So for the host, all I need to do is specify the container name that the MySQL application is running in. So this is going to be equal to MySQL simply. So if the container name was called DB, this would be DB. Okay, let's just make sure that is clear. So a host in general just tells the application where to look. In this case, look for a MySQL instance inside the MySQL container. All right, the database password is going to be password. We're just copying over all the environment variables from earlier, basically converting these terminal commands into Docker Compose fields, thereby streamlining the process of running both services at once. All right. And the port mapping, we can just copy over here. I'm going to make all these into strings. All right, wonderful. Now, what I can do is instead of having two separate terminals running two separate containers, I can simply say Docker compose up. It seems that I've forgotten a field depends on. So the Flask app container depends on the creation of a MySQL container first. So here what we can do is reference the MySQL container. And this ensures that the MySQL container is created first, followed by the Flask app container, which depends on it. So now if we call Docker compose up, it starts by creating the MySQL container, first pulling the MySQL image from Docker Hub. All right, and it ran both of them at once. That is just amazing. All right, so our Flask application, which is supposed to connect to the MySQL instance, is running on port 8000. Let's make sure that it actually is. Beautiful. How easy was that? Docker compose up. And now what I can do is on a separate terminal, I'm going to create a new terminal. And now I'm going to call Docker compose down to stop both containers. This should take some time. All right, if I say Docker ps-a, not only does it stop both containers, it destroys them. So now if I go to Docker images, I've got my Flask MySQL image, the MySQL server image. I can delete both of them by saying Docker image remove, Flask MySQL tagged latest, Docker image remove, MySQL server tag 8. All right. How easy was that? We were able to run a multi-container environment with a MySQL container, a Flask application container, and then once we were done, we were able to destroy both containers just as easily. So I hope you can see how Docker Compose can really simplify your workflow in working with containers. There's still one more thing we have to do in that the data, whatever data we end up saving to MySQL, won't actually persist because once you destroy the container, boom, the data is gone. In chapter 10, we're going to deal with this issue by using volumes. I will see you there. In the final chapter, you will connect MySQL to a persistent volume. The default behavior of MySQL is to save its data inside of var/lib/MySQL. If you destroy the container, you destroy the data inside of it as well. The solution is to create a persistent volume. A volume claims space on the computer itself, your host machine. You can then mount the persistent volume onto a path where MySQL stores all of its data. It follows that any data that gets saved into this path will be redirected to the volume itself, thereby claiming space inside of your system. If you destroy the container now, the data will survive inside of the host machine. Let's have a look. All right, on to the final chapter. Let's drag the final starter project from our lessons folder into whatever editor you want to use. Zooming in a little bit. So here we have a Docker file that's already been made for us. You're welcome. Let's create a new terminal, and here we're going to create an image that you can call whatever the heck you want. I'm going to call it grade submission version 0.01, and we will create an image from the Docker file at the current directory. All right, then we'll say Docker images to quickly access its name, because here we also have a Docker compose file that creates two containers, very similar to the setup that we had before. One container that runs an instance of MySQL, and another container that's going to run based on the following image. Okay, and here we have two fields called volumes. Comment them out for now because they're going to mess with our run. For now, what I want to do is just run both containers as is. So if I say docker compose up in the presence of a docker compose file within the same directory, it's going to create both services inside of a docker compose environment. This might take a while. All right, so here we have our Flask app running, our MySQL instance running as well. I'll go to localhost 8000 to access my application. Oh, it's running on port 8080. All right, I think I'm zoomed in a bit too much. I'll submit a grade for Harry. In potions, give him an A minus. Everything is perfect so far. But now, what happens if I say docker compose down, thereby stopping and destroying both containers? So our Flask app saved Harry's data into the MySQL database, but if I destroy that container alongside all the data inside of it, can we expect the data to reappear when we restart the process? Probably not, but let's find out nonetheless. So I've destroyed both containers. Now I'm going to restart the process by calling docker compose up. It will recreate the MySQL instance. All right. Notice how the MySQL service gets invoked first because our Flask application was depending on it. Anyways, we're going to go to grades, and the grade that we submitted before does not exist anymore. All right, so this makes sense. The container that originally had the data was destroyed. And to prevent data from being lost, under the field volumes, we can create a volume named UDB. Just like that. You can call the volume whatever you want. This volume, UDB, will take up space inside of your machine itself, inside of your host computer. Under the MySQL container, I'm going to remove this comment, press enter, tab of space. Here, I'm going to define or mount the new DB volume onto the path where MySQL stores all of its data. So remember, that's var/lib/MySQL. It follows that any data that gets saved to this path will be redirected to the volume itself, thereby persisting on our host machine. So if we destroy the Docker container, the data will still live inside of our computer itself. All right, now, if I run docker compose down to destroy both containers, it's going to take a few seconds. I'm going to call docker compose up again. Beautiful. I'm going to save some data to the database. We'll say Harry, Oceans, A minus. All right, let's save some more data. I'm going to say Hermione, arithmancy, give her an A plus. We'll say Ron, give him a C minus, and I don't know, Quidditch. Okay. Now I'm going to stop the containers. I'm going to destroy both containers. We don't really need to destroy both containers, only the MySQL one, but whatever, they're both running in tandem. Now I'll say docker compose up to recreate both containers from their respective images. Okay, I'm going to refresh the application, go to grades, and the data survived. Beautiful. We're almost done. Let's reclaim the space on our computer because we don't want this data to actually save on our host machine. This is just dummy data. So what I can do is say, first and foremost, docker compose down. We need to stop and destroy all containers that are currently running through docker compose. This might take a few seconds. Okay. And now we're going to say docker images, docker system prune -a. Checking our images again. Those are all gone. So we've removed our images, we've removed our containers. We haven't removed the volumes yet. To remove volumes, we can say docker system prune -a --volumes, and that should delete even more data. That deletes all anonymous volumes. Hey guys, sorry for the interruption. This is Rand from the future. So the reason this didn't work is because the volume we created, newDB, isn't an anonymous volume. It's a named volume. And the way to verify that is we can say docker volume ls to list all the named volumes. And this is the volume that we need to remove. So now what I'm going to do is say docker volume rm, remove the volume with this name. And it should be gone now, docker volume ls. All right. So I'll let you get back to the main course. See you there. All right, this pretty much wraps up the Docker course. We've covered almost every single important topic. If you're feeling confident, I could not be happier. That is what this course is intended to do, but you're not done yet. On my website, Learn the Part, I have exercises that are connected to all the workbook starter projects that are inside of your course resources. So make sure to go to the link that I will leave you inside of the video description. Once you enter the link, it should present you with a bunch of exercises that are very, very relevant to all the course material that you learned. I highly recommend that you do all the exercises, solve all the workbooks inside of your course material, inside of your course resources, because it will really help you reinforce the concepts that you just learned. Sometimes you learn something, it may be very easy, but it's also very easy to forget it. But if you actually practice and apply these concepts, then it will really insert itself into your brain. So, thank you for doing this course. Make sure to do all the exercises, and I will see you in the next video.